Hi. Ignore that first couple of minutes. That's fine. A few technical issues is expected. We're still relatively new to this. So what you missed before was me saying hi. This is the August edition of CyberSciBar, coming to you again virtually because it's much more fun having all this technology to deal with, as you can see. And I also just wanted to remind everyone that tonight's event will be recorded. So if you want to watch back me being really awkward on camera there for a couple of minutes, you can certainly do that. We'll be adding tonight's talk to our YouTube Palace of Science page. So you can watch tonight's talk and all the talks we have recorded over the last few months of lockdown as well. We're getting a wide variety of talks going up there now. We're going to continue to add all of our future talks where possible as well. So many of you will know the drill, aside from the technical issues. Tonight's talk will last about 30 minutes, and then we will take a 5-minute break, and then we'll be back for a question and answer session. So if you do have any questions for our speaker tonight, then you can put them into the chat box, or if you just have any comments or thoughts you'd like to share, please put them into the chat box and we'll come to them at the question and answer session at the end as well. So I'll be back again, hopefully, barring any more technical issues at the end of the talk. But for now, I'm going to hand over to our speaker for tonight. So he is a chemical engineering researcher at Newcastle.
So hello again, hopefully you can hear me now. So thank you very much to Palace of Science for the introduction and for the invitation to speak with you all this evening. It's quite different doing this from home, as I'm sure you can all imagine. It'd be nice to be in a pub somewhere and be talking to you like I would normally do these talks, but it's what we can do at the moment and I'm looking forward to it. And I hope that you all take something from this talk. So I'm just going to get straight into it. So first of all, a bit of a disclaimer. This is a public talk. Normally I would be doing this in a pub, so I'm not representing my employer, research funders, anything like that. This is just my views that I would say over a pint in the pub to somebody else. The purpose of the talk, the thing that I really want to get across is the scale of the challenge that we're facing in terms of climate change and CO2 emissions and the urgency of doing something about it, about dealing with it. So if there's anything that you take away from the talk tonight, that's what I hope it is, the scale and the urgency of the problem. And then a final point, it's always quite hard to pitch climate change talks at quite the right level. It's something that's always in the press often, so everybody has some awareness of it. So I apologize if some of the opening content you're already aware of, but hopefully towards the end I'll get to some more technical content that'll be interesting for everybody as well. And it still is growing. It's a little bit more complex than that. If we look here, so in the green sort of color, you've got the world's population, and the pink purple kind of color, that's the rate of change. So if you look from around 1800 to about 1900 or so, in the same amount of time it took the world to go from 1 billion to 2 billion people, we've then gone from 2 to approximately 8 billion, which is where we're roughly at now. And you can see that it's projected to continue growing until around 2100, but at a slower rate and a declining rate. And nonetheless, we're going to increase towards 11 billion people by the year 2100. But that change isn't consistent around the world. So if we take Europe, where we are at the moment, or where I assume most people watching this are at the moment, we're going to go from around 20% of the world's population to approximately 10, a little bit less than 10. Whereas if you look at Africa, it's very much the opposite, gone from around 10% of the world's population, and it's projected to grow to around 40% of the world's population. So the point is that the world's population is growing. It's growing a little bit slower than it was, but it's different around the world. And that's important because people in different parts of the world will therefore have different needs as we move forward in time. The second point that I want to make is that we are still predominantly a fossil fuel society. It's very easy to look at the news, look at the press, and see things around, for example, wind turbines or solar energy, etc., and think that we are, the world is now powered by wind. That's very much not the case, and I've got a few slides on that. So this is global fossil fuel consumption from 1800 to about now. If you look at the first 100, 150 years on that, around the Industrial Revolution, you can see that the world, the grey colour, was entirely powered by coal. We then discovered oil, and off the back of oil we discovered gas, and you see this sort of exponential increase in our consumption of fossil fuels, which, if you remember back to the first slide, kind of ties in with the idea that the world's population was going through this exponential growth. We have to power the things that we're doing. So the obvious question at this point, I mentioned renewables, but what about renewable energy? We see things in the news all the time about, a new record has been set about how much wind power generation we had in the UK last week, and in Europe there was this big percentage of energy produced from solar or renewables, etc. That's not really the case around the world still to this day. So if you look at this is energy consumption by source. So if I showed you this as energy generation, it would look quite different. Energy generation is that it's, for example, a windy day, we're turning a wind turbine and we produce lots and lots of energy. But if everybody's at home sitting doing nothing, they're not got the TVs on, the kettle on, etc., or they're not charging their electric car, that energy is not necessarily being used. So this is consumption. This is what we actually finally consume, finally use. And you can see that the first bottom third approximately is oil, a good chunk of coal, good chunk of gas, and then you get into nuclear, hydro, wind, biofuels, other renewables. And you're around 85% at any given time on average that the world is powered by fossil fuels still. And then you've got that remainder, you've got some nuclear and some renewables. So on the order of 10, 15%, something on average over a given year at the moment, we're being powered by renewables. So that sounds good. You see that in the news, 10, 15% renewables, that's great. But the opposite of that is it's 85, 90% fossil fuels. So we're still predominantly a fossil fuel driven society. So the third point to sort of set up the whole talk is that fossil fuel use drives CO2 emissions, and CO2 emissions therefore drive climate change. And I'm not going to go into a lot of detail on this point. I mean, we've known since the 1800s that CO2 and other gases will absorb infrared light, and therefore if we coat the planet in a blanket of it, it's going to heat up and warm, etc., etc. It's pretty simple chemistry. It's been known for hundreds of years. And the other side of this is obviously if you burn carbon in the presence of oxygen, you get CO2. So it's all pretty simple, so I'm not going to go into that in too much detail. But what I will talk about is carbon dioxide emissions and where they come from. So if we look on this plot, this is a little bit out of date now. It's until 2014, but it's much the same now. This is the CO2 emissions by source or by sector. So this big blue bar, big blue chunk at the bottom, this is electricity and heat production. So this is burning gas, for example, to put electricity in the grid to keep the lights on at home. Then you've got transport, so that's things like cars, aviation, shipping, rail, etc. You've got manufacturing industries and construction. So I'll talk a bit more about this later on, but this is essentially cement and steel production. And there's emissions associated with this production of cement and steel that have nothing to do with the power or the energy input to do the process. It's just inherent to the chemistry of the process that we do currently. So it's quite hard to imagine how we could change that. And then you've got some other sectors that make up the rest. What does this look like in terms of CO2 in the atmosphere? This is where the CO2 comes from, but then what does it do in terms of when it's in the climate, in the atmosphere? So you can see in this plot, we've got two different sources of data. You've got the blue line and then the orange line, and they overlap a little bit. And I'll talk about the map in a second. So the blue line, this is from ice cores. So you basically drill down into it says here in the East Antarctic, you drill down and you bring up a large core of ice, and in that you find dissolved gases. And those dissolved gases give you a history of what was in the atmosphere at the time. So if we look at CO2, you can back calculate how much CO2 was in the air at a given time in history. So you can see for a very long time, thousands of years, that there was a pretty stable amount of CO2 in the atmosphere, around 280 parts per million, which is the unit of concentration. And then you see again around the time of the Industrial Revolution, you see this shoot up the way and cross 400 ppm, in the last few years. The important point I'd like to make on this graph is that you can see that the blue and orange data overlap. The blue, as I said, is ice cores. The orange is a direct measurement of the air. You just measure how much CO2 is in the air by a separate technique. But the fact that they overlap gives you really high confidence that both measurements are correct, and that we're very confident that the level of CO2 in the atmosphere is rising. So what's the impact of that? You can see on the map here, this is color scale this is temperature change, average change in surface temperature from 1900 to 2012. And you can see that all around the world, the vast majority of places have warmed. And that's anything from 0.2 to 2.5 degrees. If you look at, for example, parts of Russia, they've already seen 2.5 degrees of warming. If you look at, for example, parts of Europe, you've got about half a degree. But on average, over the whole globe, you've got roughly 1 degree of warming so far. There are some areas that have cooled, but the vast majority of the areas around the Earth have warmed up. So a question might be, how much CO2 can we release going forward to get a certain amount of warming? And obviously that warming has potential catastrophic consequences for society, for the migration of people, for plants, land, animals, flooding, etc. All these things that you see in the news. So in this plot, you've got the carbon budget, the remaining budget that you're allowed to put into the atmosphere to get 1.5 degree warming, or rather to stay under it. And it's only a 66% chance of staying under it. So there's a big error on these numbers, but there's also a large number of studies. You can see about 10, 12 studies on the left-hand side. And they sort of coalesce, if you look at the bottom x-axis, years of current emissions, they sort of coalesce around 5 to 10 years. And that tells you that we can keep doing what we're doing right now for another 5 or 10 years until we guarantee that we have 1.5 degrees of warming around, on average around the globe. You'll also note that some of the bars actually go to the left of that zero line in the middle. And what that says is some of the models actually say already we've released too much CO2 to go beyond 1.5 degree warming. And that's because there's a lag. If you release CO2 today, you'll get warming some point in the future. There's a time lag between the cause and effect. But what that tells us is that we're really sort of close to this 1.5 degrees. It tells us that these studies are not perfect, but on average, they coalesce around, say, 5 to 10 years or so. So I'm going to take 10 years as my limit as we move forward in the talk in terms of what can we do to stay below 1.5 degrees. So I haven't talked about any other greenhouse gases. It would take too long if I did that. There are other greenhouse gases, but CO2 is the most important one because we release so much of it and it is pretty good at warming the planet. There are other gases, methane, for example, that are more potent. They'll warm the planet more, but we release a lot less of them. So CO2 is the biggest driver of climate change. So the obvious question is, what can we do about it? Essentially, you have two options. You can avoid CO2 entirely, and I mean entirely, and I'll get into that in a second. And this scenario would be what you would call gross zero, so zero input of CO2 into the atmosphere. And one example I've given there is you would use renewable energy sources. Your second option is that you continue some of the processes that produce CO2 in some way, and I'll explain why I think that will happen. And then you need to capture the CO2 that you were going to release into the atmosphere, or capture it once you've released it into the atmosphere, and then go ahead and store it somewhere else that won't cause a problem, but it won't warm the atmosphere, or reuse it for another purpose. You might turn it into something, you might transform it. So if you want to picture what that looks like, if you think of a bath and you think of filling the bath by turning the tap on, and you don't want to overflow the bath. So that's your input of CO2. And what that means in this context is if you want gross zero emissions, what you want to do is you want to turn that tap off entirely. So zero CO2 emissions. Because if you keep filling the bath, at some point it will overflow. And that's proportional in this sense to warming of a certain temperature, 1.5 or 2 degrees. The other option, as I said, is to have net zero emissions. So you continue some input. You probably want to slow that input. But at the same time, you pull the plug and you remove CO2. And this is net zero. So you balance the input and output of CO2 by capturing, removing it, storing it, sequestering it, etc., but just not letting it go into the atmosphere. So if we talk about scenario 1, to start with, this is the gross zero emissions. What does that actually mean in principle? So that means 100% renewable energy. No burning coal, no burning oil, no petrol in your car. And it means powering everything from renewable energy. So that includes air travel. I added that in because I saw a news story recently about the first battery-powered plane. But from the calculations and things that I've seen, it's unlikely that we're going to get to a point where we could power a passenger jet, a large passenger jet. So 100% renewable energy. Fine, admirable aim, and we should move towards that. But how quickly can we do that? It also means no cement. To produce cement, we have to take calcium carbonate or carbonate minerals, we heat it up, we get the oxide, but that releases CO2. It's inherent to the chemistry of producing cement. And cement is something that we don't often think about, but it accounts for quite a large percentage of the annual CO2 emissions. It's something on the order of 5% or so of CO2 emissions around the world every year. And one point that brings that into focus is that, for example, in China, there's been more cement introduced in China in the last 10 years than there was by Britain in its entire history. So again, you've got to think around the world about all these different countries and what kind of stage of development they're in, what are they doing currently. Same kind of story with steel. You can't make steel without the coke that you get from coal. So again, it's inherent to the process of manufacturing it that you'll get CO2 emissions. Similar story with plastics, similar story with ammonia, which we use to fertilize crops, etc., etc. I could keep going. There's lots and lots of processes that CO2 is an inherent product. But the biggest point of all this, even if we could imagine a future where we want to do all these things, and that's an admirable goal, and we should want to do some of these things at least, the point is we would have to do all of this in the next 10 years if we want to stay below 1.5 degrees. And we can debate and argue about 1.5 and 2 degrees, etc. later on. But the point is, can you imagine a world that looks like this within the next 10 years? I find that quite hard to picture. So I'm getting a lot of background noise from somewhere. If the technical, there we go, thank you, that's gone now. So one point that brings this into particular focus is the fact on the last slide that I said 100% renewable energy. Currently, or sorry, in 2017, what we had was around 10.5% renewable energy generation. So this is renewable electricity, this is heat from renewables, transport from renewables, it's the whole thing. And again, it's how we power the world, is the whole holistic picture. It's around 10.5% in 2017, and the projected growth, in this case by the International Energy Agency, is that by 2023 we'll be at 12.5%. So that sounds quite a long way off of 100% renewable energy within the next few years, bearing in mind that we have this sort of 10-year target if we want to stay approximately at 1.5 degrees warming. So if I go back to my two cases before, you've got the option to avoid CO2. And I'm not saying that renewables are a bad idea. Not at all. They're a very good idea. But are they something we can do quick enough to get to a scenario that limits warming to 1.5 or 2 degrees? I would say that's a doubtful thing. So that leaves us with option 2, which is to capture CO2 and store it or reuse it. So I'm going to deal with reuse first of all. So just to remind you, what that means is that the CO2 that we produce and put into the atmosphere, we need to capture it, take it back, and do something with it. So we still have some processes going on that produce CO2. So what does that look like in practice? So it means that we still focus on developing as much renewable energy as we possibly can, but all of it is captured and separated and either reused or stored. So as I said, I'll deal with use of carbon dioxide first of all. So essentially, you've got two pathways to go. You can either use CO2 as it is directly, or you can transform it into something else. So if I go with direct use, first of all, you can use CO2 to carbonate a beverage, for example, a beer, or you can use it to push oil out of the ground in a process called enhanced oil recovery. And that's kind of the two major uses of CO2 directly at the moment. Enhanced oil recovery, that's obviously a bit of a problem because you're bringing up more oil and you're going to make things with it. You're going to burn it. You're going to make it's fossil fuels, right? So you just produce more CO2 in the process if you use it in the way that we currently do. So that's not the best idea. If we then try and transform it into something else, you could think about making materials, chemicals, you can make plastics, you can make solvents, you can make minerals, you can make fuels with it. Fuels obviously have the problem that you typically burn the fuel and you release more CO2. So in some of these cases, at best, you kind of close the loop, but you don't actually remove any CO2 from the air. And probably the major problem with this is that if we took all of our CO2 emissions, the vast quantities of CO2 that we produce every year, and tried to make these things from that CO2, we would very quickly drop the value of all these things to close to nothing because we produce so much CO2. And that point is highlighted perhaps most by these two numbers here. So currently, of all the CO2 that we produce through burning fuels and transport, etc., less than 0.5% of that is actually used to manufacture anything else. And in the future, it's predicted, and this was from a report by the Royal Society, the potential and limitations of using carbon dioxide. It's around 5%, less than 5%, that's predicted in the future because of the size of these markets, the energy input required to transform CO2 into other things, the emissions associated with it, etc., etc., etc. It's around 5%. So use of carbon dioxide that we've already emitted is, again, it's a valuable thing to do, but it's not going to deal with the problem at the scale that the problem exists. So that moves us on to carbon capture and storage. So rather than reusing it, can we store CO2? So this diagram kind of shows you this process overall. You have some sort of fossil fuel process or a large stationary source of CO2. So it could be a chemicals plant, it could be a power plant. But the point is that you have some material in there that separates the CO2 from the other gases. For example, oxygen or nitrogen, we have no problem with just letting that go into the atmosphere. They're harmless. So it separates the CO2. We get a concentrated source of CO2, and that's really important because we don't want to waste the storage space. And it's also harder to compress a CO2 mixture with other gases. You then transport that CO2 and you pump it underground into something like a depleted oil and gas reservoir. So what that means is you've already extracted all the oil. And what you actually do when you extract oil is you pump water in afterwards. If you don't pump a liquid in there afterwards, it will collapse. So what this essentially means is pumping CO2 in there instead of water and leaving it there for a very long time. And we know that these places have stored hydrocarbons and other fluids for millions of years. So we have very good confidence that if we do that, it'll stay there. And a couple of quotes here that kind of highlight the importance of CCS. So the European Commission Long-Term Strategic Vision said that all of their pathways to get to less than 2 degrees warming include CCS. And without it, it would cost 70% more. And then the Committee on Climate Change, this is a UK body now, they said it's a necessity, not an option, for reaching net zero greenhouse gas emissions. One of the reasons that we think this is such a good idea is because we have annual emissions at the moment of around 36 gigatons. It's probably a little bit more now, but between 35 and 40 gigatons of carbon dioxide every year we put into the atmosphere. Now, a gigaton is 1 billion tons of CO2, so it's a huge volume of CO2. But these locations, whether they're old oil and gas reservoirs or saline aquifers or coal seams, big underground geological locations, they have the capacity to store CO2 for many hundreds or thousands of years at the current rate that we produce it. So we certainly have the capacity to do this. This is what on the left here, this is what it would look like. You have a pipeline, you drill down through something called a cap rock, and this provides, on the plot on the right, this first purple coloured bit, the structural and stratigraphic trapping. It's just this big rock over the top that keeps CO2 in place. With time, you can see the red arrow in the plot, you have increased storage security because you access other storage mechanisms. So one of these is residual CO2 trapping. So this is as CO2 migrates through the porous rock, it might hit a pore that's closed, a dead-end pore. It might get into a very small pore and then it can't escape again. So this is residual trapping. You then get solubility trapping. So this is CO2 dissolving into the water that's present in these locations anyway. So it's kind of like making San Pellegrino underground. It's making fizzy water underground. And eventually you get this thing called mineral trapping, and I'll come back to this later as well. This is the reaction of CO2 with the water, with the rocks that are present to form a new carbonate mineral, locking CO2 away for many thousands of years in a very, very secure way. This slide shows what we're currently doing, or what we were currently doing in 2018. I don't think it's significantly different now. But the point here is that all of these dots, all of these coloured dots represent a carbon capture and storage plant around the world. So it's in different stages. You can see the key in the top left. You've got identify all the way through to operate. So red means we're thinking about doing it, we're planning how to do it, and you get all the way through those stages until you're actually doing it. So you can see the biggest concentration of currently active carbon capture and storage plants is in the United States. But one of the problems is that they're actually doing the process I talked about earlier, where they're directly using the carbon dioxide to bring up more oil. So that's not actually very helpful. It's helpful in terms of incentivizing CCS because you get a profit. It's helpful in testing the technology because someone's willing to take the risk, as in the cost risk. And overall, it's not very helpful because it doesn't really lock away CO2 emissions. You're bringing up more oil. But the biggest problem, if you look at the scale bar on the bottom left here, you've got this, got these letters MTPA, and that means megatons per annum. So every year they're locking away something around 5 megatons per year. Megatons is 3 orders of magnitude smaller than gigatons, and it's gigatons that we emit into the atmosphere every year. So currently, the amount of carbon storage that we're doing, or carbon capture and storage, is literally like a drop in the ocean compared to what we produce. It's 3 orders of magnitude difference. So this, if you like, lack of action or slow action is leading us to the fact that simply capturing most of the CO2 we emit, once we do that, we're not even anywhere close to that yet, but once we do that, it won't be enough because it only slows the rate of release. Any capture process for CO2 only captures around 90–95% because it's technologically or technically hard to capture 100% of something in a mixture. So there's always going to be a little bit of CO2. And that doesn't even account for things like cars, planes, etc., things that are much more mobile, dispersed, and very hard to capture CO2 from. But the point is, if we want to stay below 1.5 or 2 degrees, at some point we're going to have to go beyond just capturing the CO2 that we're pumping out of large stationary sources and actually pull it directly out of the atmosphere, out of the air, because we have these dispersed sources and because we haven't acted quick enough, and also because we set these targets of 1.5, 2 degrees. And some models tell us that we've already emitted so much CO2 that we can't keep below those limits without actually removing it from the air. So you can see that in this plot. You can see the black line. This is business as usual. We can remove a lot of CO2 emissions by what they call in this plot conventional abatement. So, replacing with renewables, doing some CCS, building nuclear plants, etc. But at some point around 2050, you see that blue color goes below the red line. That means that we need to start pulling CO2 out of the air, out of the atmosphere. So at some point in the future, around in this plot around 2070, we become net zero. And that allows us, this is this idea of you still produce a little bit of CO2 in the grey that goes towards the end of the century, but you have to make up for it by pulling it out of the air. And that allows you to balance the temperature. So what are the options for doing this, for pulling CO2 directly out of the air, or as the title of the talk says, scrubbing the sky? So there's 10 options on this slide. I'm only going to talk about 2, but this is from a website, Carbon Brief, so you can go and have a look at that afterwards if you want. There's lots of different processes, but the 2 I'm going to focus on are direct air capture, and that is literally sucking the CO2 out of the air by processing large volumes of air, and afforestation and reforestation, which is quite simply just planting trees and allowing photosynthesis to take up CO2. So if I start with direct air capture, this is a very new process. There's only a few examples of it working around the world. There's a lot of research going into it, and it's very, very expensive. And the reason it's expensive, or one of the main reasons it's expensive, is that you have to process huge volumes of air. One prediction would suggest that if we only used direct air capture to control our temperature to below 2 degrees, ignoring all the other processes, all the other changes, if we just used this technology, it would take 25% of the world's energy production by 2100. That's obviously a huge amount and unacceptable in terms of power demand. By contrast, if we just planted trees, we wouldn't be able to do it. We wouldn't be able to limit to below 2 degrees. And there's some numbers here from a recent paper that was published in Science. So essentially what you would have to do if you wanted to really go for this is cover 10% of the Earth's non-urban and non-crop land surfaces, which is equivalent to the size of the USA and China together, to capture and lock away about 20 years of emissions. But there's another problem with that. It takes 50 to 100 years to actually do it, so you're always sort of chasing your tail and trying to catch up. The point being that none of these technologies alone will be enough to solve the problem. We're always going to have different cases where different technologies are going to come out and win. I'm going to focus a little bit more on direct air capture, simply because that's where my research is at the moment. I've just got a couple of slides on some of the more technical details of it. So it's been described as one of the 7 chemical separations to change the world for the reasons that I've already said. It's a very challenging thing to do, but it's likely to be necessary in some way in some locations. But one of the reasons it's very challenging is that if you look at that slide there, all the different dots, that's supposed to be representative of a mixture of air. So all the colorless dots are nitrogen or oxygen, and then the 2 red dots, they're CO2. So what you need to do is you need to design a process and a material that looks at all of those one by one, goes through them and picks out that red one and says, that's the one I want, and captures it. Now that's really difficult to do. In a power plant, for example, by contrast, you have approximately 5 to 15% of your gas mixture is CO2. In this case, it's 400 parts per million. So very, very dilute. So that leads me into some of the challenges. One of the major challenges is the energy input to simply move that air. You need to move that air over a chemical, over a sorbent or a membrane to separate it. And that takes a huge amount of energy just to process all that air. As I said before, if you rely only on this technology, it would take 25% of the world's energy production in 2100. The kinetics and the thermodynamics is also a problem. Any very dilute material, the speed of the reaction is going to be very slow. It just takes forever for the chemicals to find each other, essentially. Thermodynamics, you've got another challenge. You're trying to bring something from a very, very dilute source up to a very concentrated stream so that you can then process it, reuse it, store it, etc. And as I said before, you don't want to store all this other gases that are harmless. And then this leads you into this final challenge. The amount of material you're going to need, how costly is that material, the capital costs for setting up the plant, operating costs, etc. So it's extremely challenging. But institutions like the Royal Society, Royal Academy of Engineering, amongst other negative emissions technologies that were on that previous slide, they all suggest that significant action is essential starting now for the reasons that I've given throughout the talk. So just a few points on some direct air capture processes that are actually operating currently. I've picked two companies here, Carbon Engineering and Climeworks. So you can see if you look at the images on the far left, first of all, both of them have very similar designs in the sense that they have a large bank of fans. And that's a consistent design across direct air capture for the reason that you need to process this large volumes of air. So you need this big surface area to pull all this air through. And you have to have some sort of power input, as I said, to drive all these fans. And then both of these examples, Carbon Engineering, if I take this first, they've got a process where they basically pass CO2 over a liquid. And this liquid has a high selectivity for carbon dioxide. It reacts. They then add something to the liquid. They precipitate out a solid. They take the solid, they heat it up, and then you get the CO2 back. And now their process, it obviously requires energy. All these processes require energy. What they've done is they use cheap and abundant natural gas to drive the whole process, and they capture all the CO2 from that as well. So overall, you get net negative emissions, and you process all this air. Climeworks have gone for a slightly different approach. They use a solid material that is very selective for reacting with CO2. And they use, if you like, waste heat or good sources of energy, clean energy. So they use geothermal in the image that I've got here. There's also another example, a different type of plant, but in this case, they're using geothermal energy. And they use the heat from that to drive the whole process, to do the chemistry, to power the fan, etc., etc. And they pull CO2 out of the air. They make a concentrated source. They mix it with water, and then they pump it underground in the sort of storage process I showed you before. In this case, it's even more clever because they found a location where they have basaltic minerals. And what that means is that that mineralization stage that can take hundreds or thousands of years normally takes place in 1 or 2 years. So they lock away this CO2 very, very quickly. Problem being, it only works in certain locations for that specific type of storage. Interestingly, I thought I would add this on the slide, the pictures on the bottom left, you can pay companies like Climeworks to lock your CO2 emissions. They'll suck CO2 out of the air and store it for you. For example, if you want to take a transatlantic flight and you want to reduce your carbon footprint, you can pay them and they'll suck out a certain amount of carbon dioxide to make up for your flight. As I've said, these things are extremely expensive. We would need to do this on a massive scale. It's not going to be a technology by itself alone that's going to solve all these problems. It would require a huge amount of resources in terms of, well, different negative emissions technologies require different resources, but it's always consistently land or water or energy, etc., etc. And the most important point is these technologies are not a silver bullet. These aren't technologies that we can just do nothing now, forget about our problems, kick it into the long grass, and then turn these machines on in 50 years' time. That's not how they should be thought of. They should be thought of as helping us to achieve net zero once we've reduced most or the vast majority of our emission sources. And that just leads me on to my final conclusions. So point one is that we should absolutely be pursuing renewable energy technologies and accelerate their deployment. But we have to be pragmatic. We have to remember that we're still approximately an 80% fossil fuel driven society. So it's not like these technologies are just going to spring up tomorrow and help us get to zero very, very quickly. They are very important and we will need to use them and we should use them, but they're not going to get us there quick enough. So that leads me to my second point. Any large stationary source primarily should be replaced by renewable energy. But where they can't be, for example, certain types of power plant or cement production, steel manufacture, etc., we should be capturing the CO2 emissions from these places. And then we should be storing it. We can reuse some CO2 to produce other things that we need, but realistically we need to be doing storage on the scale of gigatons per year. So 3 orders of magnitude more storage than we're doing currently. And there's initiatives in the UK, for example, to start doing that. Final point is that we should be researching and developing technologies now to remove CO2 directly from the atmosphere, so-called negative emissions technologies. As I showed in that plot, we can't really envisage a society that has no CO2 emissions, currently at least, and certainly not at the pace required to keep us below 1.5 or 2 degrees. And that's highlighted by this point here, the International Panel on Climate Change. They showed that in their modelling, for example, 101 of their 116 pathways to get to around less than 2 degrees relied on the use of negative emissions technologies. So just a couple of slides to finish. So first of all, some resources. I used quite a lot of data from Our World in Data. This is a great website. You can find out lots of information about energy and lots of different things. International Energy Agency, the Intergovernmental Panel on Climate Change. I also use Carbon Brief, etc., etc. But the point is that there's a lot of information out there that a lot of different people have put time and effort into to try and tell us and our politicians, etc., about what we need to do to deal with this problem at the scale that's required. And then my final slide is just thank you if you've decided to tune in. I always appreciate these kind of interactions. I'm looking forward to the Q&A shortly, and just a couple of little adverts there for my social media if you'd like to interact with me in any way in the future. So thank you very much for your attention.
Thanks, Greg. That was great. And I also want to say a particular well done for remaining so professional. What the viewers at home won't have realised is that our incredible technical manager working behind the scenes appeared to tuck into what sounded like a bag of pork scratchings. And I think Greg just continued like that wasn't happening. So well done.
I think I did say at one point I could hear something. I couldn't tell what it was.
Yeah, well, we'll find out at the break exactly what it was. My bet is on pork scratchings, but there we go. So for everyone watching, we're going to take a short break now, about 5 minutes. This is, of course, your chance to digest everything you've just heard. And if you do have any questions for Greg, then please type them into the chat box and we'll have a question and answer session shortly. In case anyone has to leave, I just want to put a little plug in now for the events we have coming up in the future. So the next CyberSciBar we have organised is on the 30th of September. A totally different topic. It is a researcher from the University of Sunderland talking about her work in autism, the myths and the misconceptions surrounding autism. And after that, a total change of gears again. In October, the 20th of October, we have a researcher from Newcastle University talking about her work that contributes to a larger project that is using virtual reality and gameplay to train chemical engineers. So that should be really interesting as well. So that's everything from me for now. As I said, please write your questions in the chat box. 8:20 for a question and answer session with Greg. So see you then. Hi everyone, welcome back. So we're going to get started with the question and answer session after Greg's great talk. So I can see we've got quite a few questions that have come in, so I'll just get started straight away. So the first one we have, someone is saying that carbon capture seems to be an active method of reducing carbon in the atmosphere. Is there any plausible way of making this technology part of daily life, like an add-on for trains or buses or something along those lines?
Yeah, that's a really good question. So I think one important point to make and maybe clarify is that there, if you like, there's two types of carbon capture and storage in a sense. There's carbon capture and storage that you do at a power plant, a large stationary source. And then there's this technology I've talked about, which is direct air capture, and that's pulling CO2 directly out of the atmosphere. So one of those only slows the amount of CO2 that you're putting in, whereas one of the second one actually pulls it out, it draws it down, a carbon removal technology. So just to clarify that to start with. It makes most sense to do these processes at the largest sources of CO2. It's always going to take energy to separate a mixture. I've got some orange juice mixed with water here. If I wanted to get the orange juice back, it's going to take an energy input to do that separation. So it's going to be a lot easier if you do that at a large stationary source. So for that reason, in the near term, there's not going to be small localized carbon capture. It's going to make more sense to try and replace that fuel, for example, which is why we don't see a car with a carbon capture plant in the back of it. You see a battery powered car being powered from a power plant that has carbon capture on it, because it's easier to do it in one place in a big way rather than thousands or millions of little ways. In terms of the direct air capture, which is actually pulling out of the air, that might make sense in some cases to do it in localized areas. One example might be if you were an airline, for example, and you wanted to mitigate the emissions associated with your aviation fuel. Maybe in your where you keep all your planes, you've got a little direct air capture plant. You pull the CO2 out, you make the fuel, you power your plane, and you kind of close that little loop. So it kind of a yes and no.
I see. Yeah, that makes sense. In terms of you, obviously you mentioned that a lot of these processes are going to be really energy expensive, and you mentioned something like using geothermal to sort of set it up. Is that really going to limit where you can set these operations up? Like Iceland have a lot of geothermal plants. Would that really, we'd have to do it there to make it more efficient, or is it easily like moved elsewhere?
So again, if I take that question in two parts and think again about carbon capture and storage and then direct air capture. So carbon capture and storage, for example, the UK, we have loads and loads of very well mapped depleted oil and gas reservoirs in the North Sea. So we would be in the advantageous position that we might actually be able to mitigate the emissions of other countries. And that's where you get into things like carbon credits, etc. So other countries might release their CO2 or might capture it, give it to us, and we store it, and we can sell that, for example. Or, as you said about Iceland, Iceland's in a unique position where they've got lots of geothermal energy, and they've also got the right type of minerals for making carbonate minerals really quickly. So they're in a unique position to do direct air capture. So again, there are specifics, and you need to think of it from sort of a system perspective. You need to think of the whole energy system, if you like. But you're completely right. If we think about carbon capture and storage, and this is why some people would argue against it at a power plant, is that it takes approximately a quarter of the power plant's output just to run the carbon capture part. So that then gets transferred on to somebody as a cost, right? So it would probably make sense to replace, in terms of climate change, it definitely makes sense to replace that with renewable energy. But ultimately, that's one of the big questions as well. Who's going to pay for all this?
Yeah, that's actually someone has noticed that and brought up the next question. They're asking, do you see carbon capture as a government service done by all nations, or will it be business fueled by revenues from carbon taxation or refunds?
That's a really good question, and one that I'm probably going to try and tactfully divert from answering. It's not. I mean, that's something that you get into a very political situation there, don't you? You end up thinking about. So if you take France, for example, where they put levies on fuel to try and do something good about the climate, you saw everybody out in the street campaigning against that. You can understand that if that hits the individual's livelihood, that's not a great thing, but at the same time, it's protecting the planet for the future. So there's always trade-offs in these things. There are some clever things that you can do. As I said, you can do carbon trading, you can do carbon credits, etc. You can incentivize companies to do these things. You can make products from some of the CO2 that you capture, etc., etc. But realistically, that's one of the things that's a big issue. And Perhaps the most sensible thing I can say is that the government, about 2 or 3 days ago, published their approach to business models for carbon capture, utilization, and storage. It's on the government website. I've read a little bit of it so far. I need to dig into it more, but realistically, that's one of the real things that they're grappling with at the moment. How do you incentivize this, and how do you make it happen?
So for the direct air capture, how new is that technology?
In its current form, in the examples that I showed you, Climeworks, Carbon Engineering, there's a few other companies, Global Thermostat, for example, very new. They've built these plants in the last 5 years or so. This is a very small pilot scale demonstration. The chemistry is as old as the Earth, right? You're making use of, or most of it is, you're making use of chemical processes that have existed for a long time. The carbonation reaction to form minerals, etc. It's been around since the Earth's been around. So, in that sense, it's not new. In its current form, it's a new way of processing carbon dioxide, if you like. But yeah, very, very new technologies. And another government thing in the UK, they've announced some sort of consultation process, because again, they want to release a lot of funding to start developing this technology in the UK, because all of the companies I mentioned so far, they're in Switzerland, Iceland, America, etc. We don't really have a lot of work in that area in the UK.
Okay, someone was asking something else along those lines, saying, can you describe any interesting developments from the international carbon capture and storage community? They've asked, are there any countries ahead of the UK in terms of doing that, or are we really far behind?
Again, it depends. So we've got some incredible research facilities in the UK. I'm just sort of going through in my mind all the different places I've visited through my work. We've got some great large pilot scale carbon capture facilities. We've got some, as I mentioned, we've got these great geological empty oil and gas fields that are almost just begging for us to fill them up with CO2. Some particular developments recently, there's this thing called the Industrial Clusters Challenge. And what that seeks to do and is doing is demonstrating real large carbon capture plants. So if people are interested in that, it's IDRIC, so IDRIC. If you look that up, but basically what they're doing is, if you take a large industrial cluster where you might have a power plant, a steel plant, a cement plant, etc., and you capture all the CO2 from all those different sources in one place, because these things are always typically located around each other. So, for example, Teesside would be one very close to us. We've got a lot of big chemical companies. You capture all that CO2 and then you pump it offshore in a pipeline, and that's happening now. They're starting to plan and build and demonstrate these things in the UK.
Okay, so with this technology being so new, are there any examples of big failures so far? Obviously, when you mentioned the idea of San Pellegrino underground, I mean, sounds delicious, but I also thought that sounds horribly dangerous if that escapes. Are there any examples of that sort of health and safety issues being a big hindrance?
So, one word answer, no. There's lots of really great projects around the world. There's some in Australia, there's some in the North Sea related to Norway. There's this enhanced oil recovery in the States. There's been lots of projects where you inject CO2 and then you monitor it for a long period of time. You look for leaks, etc., etc. Essentially, the answer is no, it's not a problem. The storage part of the whole process is one of the most well understood, safe parts. The challenging part is, how do you do the separation of the CO2 at the source in a cost-effective manner? That's where all the research really is. As I mentioned, these geological locations stored hydrocarbons for millions of years. So it's an important point as well. I did mention it in the talk that when you extract oil, everybody imagines that you just suck the oil out of the ground and then you leave this big cave underground, which is not the case. You actually have to inject something into it to stop it from collapsing. So these locations will store fluids under pressure for a very long time. And arguably, that's one of the sort of most well understood and safest parts of the technology.
Yeah, I suppose that makes sense. It's just with any new technology, I guess, like nuclear, obviously, you say nuclear, the big things that come to mind are the disasters that no one really expected to happen. And there's always going to be something built in along those lines. But I guess, yeah, you're right. There has been sort of a way of testing this before, what was there before, what we've put in and what we can see happening.
Yeah, absolutely. And I think one of the important points to make as well is that that's very much the case. And as I said, you can look up different places that they've done this. They've done monitoring, verification, etc., to look at this over a long period of time. But one of the important points is that we don't really have very many other great options currently. We really need to start doing this at scale. We are already doing it at that millions of tons per year, and there's not been anything close to a large scale, disaster or problem or anything like that. If anything, it's actually worked very, very well, and it's difficult to detect it leaking, etc., etc.
That's great to hear. I suppose positive news to get more people involved in future. Have you seen? I don't know if you personally have, or generally the field, a massive increase of funding in this area and interest in this area based on how urgent the need is?
Yes and no. So there was a large carbon capture and storage competition. I would be lying if I said I remember the year, but say 5 years ago, where they asked various companies, universities, institutions to build the first CCS plant in the UK and demonstrate the technology. And that was likely to go ahead either the Drax power plant or the Peterhead gas terminal. And unfortunately, I think it was literally the evening before the government decided that the supposedly ring-fenced funding would be pulled. And that had a really big, bad knock-on effect in terms of companies, their confidence in it. They'd invested a lot of time and resources to develop their plans. But multiple years later, new government, etc., the challenge of net zero, the international commitments we have with the Paris Agreement, net zero by 2050, etc., etc., we're back to a point where you are seeing these large tens of millions, hundreds of millions investments by the government, by UKRI, by research councils, etc., both into research on the more or the less developed aspects of it, direct air capture, for example. But you're seeing significant investments by both companies and the government in demonstrating these things. And again, I would just encourage people to go and look at this IDRIC, IDRIC, which is the industrial clusters, and they will be building it, they will be doing it, and they will be injecting CO2 underground within the UK in the 2020s. And that'll be our first demonstration plant. And from there, they hope that a lot of other plants will cascade from that. And then what they want to happen is the UK to be a leader in this technology, and we can help other countries do the same thing.
Yeah, definitely. And I suppose this is primarily going to be focused on the more developed countries that have the money to do it, places where, I guess, oil and gas have been extracted from, and then they can work from there.
Yeah, exactly.
We have another question, someone asking, I've heard that some forms of building materials can directly absorb CO2 and store it integrally. Is that likely to become reality, or is it all sci-fi?
No, it is reality, I would imagine. I think there are. I remember one project that I saw quite a while ago. It was cement, related to cement. So cement that over its lifetime absorbs more and more CO2. Absolutely, there's building materials that do this. But again, it's all about the scale, the pace, the challenge. I mentioned trees in my talk. And yes, you can absorb a large quantity of CO2, depending on what your definition of large is. But you can do that, but it takes a long time. So I'll use the analogy again. You're kind of chasing your tail to keep up with the pace. You're emitting all this CO2. And if your capture technology, whatever that is too slow, it's not actually going to help you very much. In principle, yes, there's building materials and all these things are very useful. But I keep going back to the point that we are going to have to do large gigaton scale storage underground of CO2 if we want to really make a dent in this.
Yeah, that makes sense. So just from your own personal research, obviously you've just been awarded this very prestigious fellowship to run your own research. What are you hoping to achieve by the end of that, if it's not too secretly guarded in terms of this work?
Yeah, no, I'm happy to talk about that. So I work with membranes for separation. So I said earlier on about this orange juice. If I wanted to get the orange and the water back, you need to separate it, right? So a lot of the current processes, what they do is they rely on a chemical, some sort of material that reacts with carbon dioxide. You then take that material, heat it back up, and you release the pure carbon dioxide. So what I work with is a membrane that will do the same thing. Now that's better in some aspects because you can just leave the membrane sitting there and it acts like a coffee filter, right? It filters the coffee grains from the coffee. So it does the same thing with a gas, and it's kind of a bit more passive. It can just sit there and allow the gases to pass through that you're not bothered about and capture the CO2. So the idea, the things that I'm working on are membranes for CO2 separation from different sources, from power plants, for example, from steel, cement. They all have slightly different conditions. But I'm also interested in this idea of direct air capture and what could you do, because it's, quite honestly, it's just a really interesting challenge scientifically as well. It's really difficult. So that kind of gets you excited as a researcher. You can do all this very useful, impactful research that will have, very sort of medium near term impact, but at the same time, can you work on something that's quite challenging and exciting and a bit out there?
Do you get any support or pushback from people working in renewable energy companies? Are they more focused on wanting to promote that, or is it really a partnered thing, which really it should be, I guess, for this to us to reach the goal that we're hoping for globally?
Yeah, you've completely hit the nail on the head there. I think people, I can't say, what it was like 10 years ago. I'm sure you had your factions, just like you had with nuclear, for example. There's all these different things. But I think now people kind of realize that, the primary goal has to really be renewables, right? You have to think in the long term that we can't just keep doing this, burning things to give us energy. It has to be a bit more intelligent than that. It has to be cleaner and greener. But at the same time, we have to admit the fact that there's large portions of the world that hasn't had the kind of industrial revolution that we've had in the same way, or they're developing in terms of massive population growth, and these people need access to more and more energy, new devices, etc. So there's a bit of an acknowledgement that there will be fossil fuels in the mix. And certainly, as I keep saying, for some of these processes, it's nothing to do with powering the process. It's to do with the chemistry of the thing, of the steel, of the cement. So some of that you just can't get rid of. So I would say that you do get some people that are in one faction or the other, but I think in general the consensus is that, renewables have to come first, but at the same time we need to keep an eye on this problem that's kind of accelerating past us at the same time.
Yeah, and I guess it's hard for people not to become so narrow-minded, and I guess the media, whichever way they fall, doesn't help. If it's focused on one thing, everyone wants that, and which is, I suppose, even in research, it's difficult to do that, really look at the bigger picture and say, I can do A, but B also has to happen to achieve this goal.
Absolutely. Yep, totally agree.
Another question just coming in. So we've obviously been talking about carbon capture, but obviously relating to climate change, that's not the only problem. Are there any current research happening towards the reduction of local nitrogen dioxide capture or reduction? Do you know?
Yeah, so as far as I'm aware, that's more of a problem related to cars and engines and things like this. I would be lying if I said I was an expert in this area. I know that people, there was the big scandal last year with VW, I think it was, related to NOx emissions. So people are always working on better catalysts for catalytic converters in cars. One big one, perhaps, is methane. I touched on it in my talk a little bit. I've seen some studies in the last sort of 6 to 12 months about the amount of methane that we're kind of leaking from pipelines in various places is actually a lot more than we thought it was originally. So that's something that people are starting to have an idea about doing something with. As I said, it's a much more potent greenhouse gas, but there's a lot less of it in the atmosphere. So I talked about CO2 being at parts per million level, methane's at the parts per billion level. So perhaps somebody out there wants a really, really difficult research challenge. They can try and do direct air capture of methane at the parts per billion level.
So you don't think any of the technology that might come from this might be transferable to other gases?
Certainly gas separations in general and a lot of the approaches that I use, membranes, adsorbents, these kind of things, yes, you can transfer the learning to other gases. But I guess the main point is that, so I suppose a bit of historical precedence is important as well, that, for example, with SO2, which is sulfur dioxide, or these kind of gases, they can be released when you burn coal, but we already have processes to capture SO2. We already did that. Or mercury, for example, you find mercury in various fossil fuels, and we already capture that because we know it's a problem. So there has been learning transferred from them, but I suppose CO2 in a way is a different problem because, first of all, there's so much of it, we produce such a large quantity of it, and it's one of the ones that, because there's so much of it, we can actually probably do something about it.
Yeah, I suppose if it's there and it's the biggest problem, then focus on that for now, and there will definitely be work going on towards all the rest alongside that. One more question. So in terms of the carbon storage, does it need to be underground? Could you also pump and store liquid CO2 in sort of deep ocean trenches?
Oh, good question. I don't know if I know the answer to that one. You do see, well, I suppose it's kind of similar to methane hydrates. You see methane frozen under the ocean, and people are worried now about that heating up and being released. I think that realistically, it's so if you're talking about just in the ocean, you're just dissolving CO2 in the ocean, which already happens, and that's a problem. It acidifies the ocean. It has problems related to animals and coral, etc. If you inject it at such a level that it might, I don't know, freeze or something, I don't know. That one sounds a bit wacky.
That's something to think about.
Yeah, I don't know. Maybe that's it. Maybe they've struck gold. Maybe that's the idea.
One final thing I wanted to ask you, something that sort of came about from this event, obviously, really interested in your work, and it's great to hear about it. A lot of the stuff I didn't know, and I trust a lot of other people out there don't know. But one thing I did notice is as we were advertising this event, we got quite a negative reaction. A lot of people being really distrusting, dismissive. I've noticed not any questions from the people that previously commented that didn't trust any of your work, but you must come up against this quite a lot. Anything related to climate change, it is a very controversial topic. I mean, it shouldn't be, but it is. Do you think that affects how you're able to do your research? Certainly from my own point of view, I'm in research as well, and I don't come up against any controversy because everyone loves honeybees.
So in terms of my day-to-day, no. Like I said, if you want to go back to like an old school chemistry textbook, Svante Arrhenius told us that CO2 in the atmosphere would warm the climate in about 1820 or something. So if you've had anything close to an education in chemistry or physics, it's not hard to imagine that global warming is a real thing. In terms of the specific technologies, yes, you get people that say, well, just plant loads of trees, and then you have to have a conversation about, well, okay, there's the pace that they'll take up CO2 and the final amount they can take up and all these things. And very often it's the detail, right? There is no simple answer. Like I said, there's no silver bullet. You have to have a diverse range of technologies that deal with certain niches, etc. So in general, does it stop me wanting to do what I do? No, not at all. Do I think that everything I do is going to save the world? No, not at all. But if all the people that work in this kind of field can make a small contribution and in some way can make a positive change, then that's great.
Yeah, definitely. Very modest of you. But no, that it's great that obviously you volunteered to give this talk tonight, and I think it's really important to bring that in an accessible way to a public audience, just to get the information out there, whether people choose to believe it or not. That's probably always going to happen, but all you can do is put it out there and hope people listen.
Yeah, absolutely.
Really?
And I think if there was a final message that I would say, it would be that, this is a large scale global problem. Individual actions are great, but realistically, we need to be electing governments and lobbying governments to be making large, meaningful, huge decisions, big decisions.
Yeah, absolutely right. And hopefully more of that will happen in time. But I think that is everything for tonight. So thank you so much, Greg. That was a great talk. And as I've said before, it was recorded and we will be adding it to the Palace of Science YouTube channel. So if you want to watch it again, or if you want to tell your friends, then you can head to YouTube to watch that. So just before we leave, a couple of things from me. I'm just being told here that there is, sorry, I'm just reading it right now, a survey we want you to fill out, I believe, a feedback form about this event. It should hopefully have been added to the chat box. So if you have a couple of minutes to fill that in, your information would be really valuable to us so we can keep bringing you events like this one this evening. Of course, we do have some more events lined up, as I mentioned earlier. So next month's CyberSciBar is on the 30th of September. A researcher from the University of Sunderland talking about autism and her work into autism. And in October, a researcher from Newcastle University talking about her work using virtual reality to train chemical engineers. Apart from that, We are Palace of Science. We have a website, we have social media, all the different social media channels. So if you want to leave us any comments or queries, then please do get in contact. And hopefully we'll see you next month. So thank you for joining us. See you.